Okay. So the next question we got on the menu today is what is the average and instantaneous rate of change? So let's first talk about the average rate of change. And we can start by drawing a graph like this. Suppose that's our y angle. Suppose that's our x. And suppose we have a parabola, maybe. Okay, average, let's make that average rate of change, let's red. So as you move from x being 0 onwards, you're going to see that the y value changes. At what rate is it changing? Well, to find the average rate of change, let's say you want to find the average rate of change between, let's call that t1 for time 1, and t2 for time 2. The average rate of change is just going to be the slope between these 2 points. Let's get some straight lines. Okay, but you see how that's not like perfectly in line with the graph itself? There's nothing really to worry about. So this is average rate of change. I call that a rock because it makes me feel like a rock star. Average rate of change. So how would we calculate that? The average rate of change is, let's actually draw some more lines in here. Shapes, lines. Okay, that would be a line, and that would be a line. So that could be y1. Oops. y1, y2. Okay, so if we wanted to find the AROC, it's we know the AROC is the slope of that little line segment. Line segment, that's a keyword. You'll do y2 minus y1 over t2 minus t1. Okay, and that seems very reasonable. You're just finding like the average rate of change from those 2 points. You're just looking at the start, the end. You know, if we were to have an average rate of change between them, what would it be? It would just be the slope. Okay, now instantaneous rate of change is, imagine we moved these 2 dots to be much closer together. Like we move that dot right here, and we move that all the way down the parabola, all the way to here, all the way down so that they're like pretty much on top of each other. That's essentially what the instantaneous rate of change is. Like when you're really, really zoomed in like this, and then like you take the AROC, maybe something like that, and that, but like something between that and that, like so close that it's like infinitesimally small. Like you probably shouldn't even be able to like differentiate them from each other from out here. But like the instantaneous rate of change is the derivative. And it's tangent. So it's a tangent line. So if I were to draw a line, the instantaneous rate of change right there, I think I can reposition this. It's probably something like that. Okay, so you see how A rock you're going to be able to see space between them. I rock is pretty much this. You find the process the same way as you find A rock, except it's like infinitesimally small, like the difference or the space between them. Okay, so how do we calculate A rock? Well, I rock. So if we know that I rock is really, really small in terms of the differences between them, we can kind of like make that a limit, right? So let's say the limit as h approaches 0. Okay, and h is basically going to be like the distance between it. You'll see very fast. So on top is going to be like y of 2 minus y of 1. Perhaps instead we could also say that this is equal to like a function of x. Okay, so what we can say here is that it's like what's immediately after minus what comes earlier, right? So if h is the separation between them, it's going to be f of x plus h minus f of x. Okay, and you see like x plus h is like extremely small, so that just means like if we really zoom in, really zoom in on here, like right maybe here at this point, I hope you can see my mouse, like at this point it might be like f of x, and like right at here would be f of x plus h, but like extremely small difference between them, a difference so small that it's like when h is approaching 0. Okay, and let's do the bottom. So the bottom in the A rock originally was t2 minus t1, so it's going to be like the same principle. It's going to be what's coming after minus where you started. So that would be t plus h, that's where you're ending up, minus t, because that's where you're starting. Now we could simplify this. Limit of h approaching 0. On the top, well, there's nothing really we can do to simplify that because, well, we don't know what the function is. So we can't really make this general that way. Oh, this should be x instead. T are just like specific values, but this was actually like a particular x value. On the bottom, you see how we have positive x minus x? They neutralize each other out of the bottom, so on the bottom it's just h. Minus f of x over just h. And this, my friends, this is the first principles equation of calculus. Derivative equation. I think Isaac Newton was one of the pioneers behind this equation way back in, a couple of years before I was born, in the 1600s or something like that. But yeah, this would be how you find your IROC. And another way of saying finding your IROC is finding the derivative. And there are a lot of shortcuts. Like, of course, you can find most derivatives this way, but there are typically easier shortcuts that you can find. Okay, so that would cover average and instantaneous rates of change. Yep, the above solution is correct, but it's just a little bit in a different path, but we came to the same conclusion. IROC versus AROC. It's like derivatives. IROC is tangent. AROC is like the connection between them. Cool.